Hello. Can you hear me? Hello. Dum, dum, dum. Hello, Ahmad. Okay, let's do this. Can you hear me? And can you see the screen? Okay. Perfect. So for today we're going to do a couple of disconnected things. There's a section from chapter 6 which is 6.4, contains some interesting identities that I want to cover, and then I'm going to look at 8.4, I believe, which is the something from chapter 8, which is the Inclusion-Exclusion Principle. Okay, so let's just begin, I guess. Few people online today. Is that because I'm late, or is there some other reason? Anyway, it doesn't matter, let's just get on with it. Okay, so let's start with something that you're probably already familiar with, that is the binomial. Hold on, I will be back. Okay, and so this is something that you should be already familiar with, I believe, which is the Binomial Theorem, which is the following. The Binomial Theorem tells you how you can expand this product, this power a plus b to the power n, right? And do you remember how to do this? You take a to the power n plus some factor times a to the power n minus 1, b to the power 1, plus then some factor a to the power n minus 2, b to the power 2, and so on, up until you reach b to the power n. Do you remember what the factor is in the first case? Do you remember what this is? Do you remember what this is? What are these terms? जी मात याद है आपको? Okay, dum dum dum. Right, so yep, exactly, NCR. Thank you everyone for responding. So this is NCR in More specifically, r over here is, so this is r equals 0, r equals 1, r equals 2, and so on, and r equals n, right? So this is nc1, this is nc2, up until you reach ncn. And so we have these terms. Now, before we move on, I want to clarify that there are some notational chain differences. So NCR is the same as if you write in parentheses NR, that's the same thing. And in your book they also use the rotation CNR. And this is all the same. This is, if you remember, all of this is just saying there are how many combinations, number of ways of selecting without any order, selecting R objects from a set of n objects, right? So in how many ways can you select n R objects from a set of n objects? And that's the theorem, right? And so my focus is not going to be the theorem. My focus is going to be some interesting facts that you can get out of this theorem. The first thing that I would like to talk about is the summation. So what if I wanted to take all of these terms, summation n k, so I'm switching to this notation, this middle notation. So I'm saying NCR, and k goes from here 0 to n, right? So what I'm asking for is essentially, I'm saying, what if I take nc1 and starting from 0, nc0 plus nc1 plus nc2 plus dot 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 up until ncn, right? If you recall, by the way, this nc0 and this ncn have to be 1, right? They have to be 1. And my question is, I want to add up all of these terms. And how can I find this sum for any n, right? And now if you look at the binomial theorem, the answer actually becomes pretty easy. So if I take in the binomial theorem, select a equals b equals to 1 in the binomial theorem, you get something interesting, which is that if I take a plus b to the power n to be simply 1 plus 1 to the power n, then on the right hand side I should get the following. If I follow the binomial theorem, now a is 1 and b is 1, right? So 1 to the power n, this is going to be just 1, this is going to be just 1, n equals to 1, n equals to 1, equals to 1, and all of these terms in a and b are just 1, so they're multiplying by 1. So all I'm going to get is the following. I'm going to get 1 plus nc1 plus nc2 plus dot 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 up until ncn, right? Which was also, by the way, just equals to 1. And so I can rewrite this as nc0 plus nc1 plus nc2 plus dot 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 plus ncn. So on the right hand side I have the summation that I was looking for, and the summation is summation k goes from 0 to n choose k, right? But on the left hand side I've gotten something extremely simple, which is, follow this, this is just 2 to the power n. So if you take a particular n and add up all of the ways that you can select 0 objects, 1 objects, 2 objects, and up until n objects, the answer is simple. It's just 2 to the power n, right? Does that make sense? Dum, dum, dum. Any questions? Any confusions? Nope. Okay. All right. What if I was looking for the series summation -1 to the power r n c r, right? And again, this is r goes from, let's just be consistent with the previous notation, so n c k -1 to the power k goes from 0 to n, right? And now this is an alternating series where the signs are changing in each term, right? And again, the solution to this comes from the binomial theorem. So if I want to find out what this series is equals to, I look at my binomial series and try to generate the series. So on every term I want a -1 to the power r, and to do that, that's really simple. I can change, so b is following the power of this number, right? And so if I choose in my binomial theorem, I choose a equals 1 and b equals -1, then I get the following. Then I should get the following. I get summation so the first term is going to be nc0, second term is nc1, let's just write a to the power 1, sorry, a to the power n minus 1, and b to the power 1 plus nc2, a is n minus 2, b is raised to the power 2, and so on up until b is raised to the power n, right? And so this is simply nc0 plus, this is 1, so I can ignore it, this is -1, so this is -1 to the power 1 nc1. Next term is b is -1 again, so -1 to the power 2 nc2 plus dot up until -1 to the power n. And so you can write this entire thing as follows. So notice there is no -1 here, but I can write it as -1 to the power 0, and over here it's -1 to the power n nc n, right? So this can be again written as summation -1 to the power k n choose k equals to 0 to n, right? And now what is this summation going to be equal to? We just need to figure out the left hand side, and the left hand side is a plus b, which is 1 plus -1 to the power n, and this is simply going to be 1 minus 1 0, so it's just 0. So if you take all of these terms and you add them, then you're going to get 0. If the sum is an alternating sum, then they're going to sum up to 0. Clear? All right, and let's try another sum. Okay, what if I wanted to take the next one to be number 3? So this is, again, we're just choosing different a's and b's and getting some interesting results. So first one is, so this one is going to be, what's the sum of the series summation 2 to the power k n choose k? And so can you think of what to pick for a and b now? What will be the value of a and what will be the value of b to find this sum? So I want something like the first term to be, I want it to be, so 2 to the power 0, n choose 0 plus, let me write it in C notation, so nc0 plus, next term I want to be 2 to the power 1 nc1 plus 2 to the power 2 nc2 plus dot up until 2 to the power n ncn, right? So what should I pick my A and B to be 1 and 1. If you pick 1 and 1, then you're going to get something like this. 1 and 1 we've already selected. A equals 1 and B equals to 1, we've already done that, and that gives us this series. There's no factor of 2 to the power k here. I want a factor of 2 to the power k here, right? So this is the factor that I want. Anyone else? A1, B equals to 2. Absolutely correct. So if I pick A to be 1, A to be equals to 1 and B to be equals to 2, let's see how that can happen. Notice that the first term is simply 1. The second term is nc1 2 to the power 1 plus nc2 2 to the power 2, and so on. And if you choose A to be 1 and B to be 2, then what do you get? You get 1 to the power n plus nc1 1 to the power n minus 1. I don't even have to write the terms with 1 because that's just going to be 1. I can simply write 2 to the power 1 plus next one nc2 2 to the power 2 plus dot dot dot, the last term is 2 to the power n. And notice that the terms do end up matching. This is 2 to the power 0 doesn't matter, nc0 doesn't matter, so this is the same as 2 to the power 0 nc0 plus 2 to the power 1 nc1 plus up until 2 to the power n. And so the left hand side gives you the answer. The left hand side simply is 3 to the power n. So the sum over here, so summation 2 to the power k of n, 2 to the power k of n choose k, k going from 0 to n is simply 3 to the power n. Make sense? Okay. All right. Okay. So I'm going to skip Pascal's identity and move on to Vandermon's identity. And this next one I'm going to do a little proof, but the proof for this one is going to be from combinations, right? So the identity is, we have an identity, let's call it identity 4, but perhaps we can call it Vandermon's identity. And the identity looks like this. If you want to choose m plus n, choose R. That is, if you want to select a set if you want to select R elements from a set of m plus n elements, then that's simply equals to summation R goes from 0 to 0 to n, I believe. Is that true? Sorry. K goes from 0 to R, and this one is m choose R minus k, and next one is n choose k, right? And so this identity is saying the following. It's saying that if you want to select, now left hand side, I'm going to prove this while I'm explaining it, right? So I'm not going to do any fancy technical proof. It's just going to be proof by, okay, so this is saying choose number of ways to choose R elements from m plus n elements. And the right hand side is saying something different. The right hand side is saying separate m and n into two different bags and select k elements from bag that contains the n elements, and the remaining r minus k elements from the bag that contains. So think of it at two different bags, right? So you're selecting k elements from n, and you're selecting r minus k elements from m, and if you add them up, how many are you selecting? R minus k plus k elements. So that's simply you're selecting r elements and a total of m plus n from m plus n. But then the question is, where did this summation come from, right? And this summation is basically coming from the fact that it's possible that you want to select one element from here and r minus 1 elements from here. It's also possible that you select 2 elements from here and r minus 2 elements from here. So basically you're accounting for all possibilities. So what are all possibilities? If you separate them into two bags, one that contains m elements and the other that contains n elements, if I want to select a total of r elements, then first I can maybe select no element from here, no element, and select all r from here. So that one will be, I'm choosing mcr, but I'm choosing no element from here, so nc0. So I'm multiplying these two possibilities because we're counting the total number of ways in this one situation. Then in the next situation, maybe I select one element from here, nc1, and the remaining r minus 1 elements from this bag, right? And so these are the different possibilities, and these possibilities can go on. So m r minus 2, but n choose 2, and so on. They could be m choose k. So if I take out k from here, then I will have r minus k from here. And so this right hand side was basically this entire sum for all of these possibilities. We were accounting that I pick 1 here, 2 here, 3 here, 4 here. And we don't have to do different cases on the left hand side, because in the left hand side the bag is all together. M plus n elements are all together, and you can just pick r elements from this bag. So that's just m plus n choose r. So does that identity make sense now? Do you understand where the summation comes from, why there is this product? Okay, perfect. So let me, should I do some more? Let me just state another one, and then we'll be done, and I'll leave theorem 4 perhaps. Let's see, do I want to do theorem 4? No, let's just skip that. So okay, let's just do corollary 4 and get done with it. Okay, so in this identity, in Vandermon's identity, if I pick Vandermon's identity, if I pick m and n, so in Vandermon's identity, select m equals n, then what do you get? You get a nice little summation. So on the right hand side you get summation n choose r minus k times n choose k. So you're selecting k elements from n and another r minus k elements from n, and what you get is, this is summation k goes from 0 to n. And on the left hand side you get, this is m plus n, so this is 2 times n, right? The left hand side was m plus n. I've chosen m to be equals to n, so this will be 2m, and let's also choose r to be equals to n as well, right? So 2n, so this is basically choosing n objects from a bag of n to n objects, right? And on the right hand side you have n, and this one is n minus k. So n choose n minus k and n choose k. And over here, if you remember an important fact is that if you have n choose nc n minus r, and if you have ncr, these are both going to be equal. Something that you might have noticed. And perhaps if you have, let's say, n is equals to 10, and if you pick r to be equals to 3, then you must have seen that 10c3 is going to be the same as 10c7. There's a symmetry about these coefficients, right? So these coefficients start from 1 and they keep increasing, and then up until some point. So if you think about what are the possibilities for 3c0, 3c1, 3c2, 3c3, these are 1, 3, 3, 1. So there's a symmetry about these coefficients, right? These are the same and these are the same, right? If you look at what is 4c0, 4c1, 4c2, 4c3, 4c4, then those are just 1, 4, 6, 4, 1, right? And so 4c1 is 4, and so there's a symmetry again. 4 and 4 are same. So 4c3 is the same as 4c1, right? So the point I'm trying to make is both of these terms are the same and can just be simply written as summation k equals to 0 to n choose k. Both of these are n choose k squared, right? So basically your sum from n equals, switch to this one, summation k goes from 0 to n, 0 to n is basically n choose k squared. This series is going to be equals to selecting n objects from bag of 2n objects, right? So you have another nice little series here, so let's call this series 4. Okay, make sense? Any confusion? Okay. All right, so if we're okay with all of this, then let's just move on and do the inclusion-exclusion principle. The inclusion-exclusion principle. Okay, let's start that off by considering two sets. So we have set A and, oh, that's nice, and set B. Set A and set B. This area is, if I want the number of elements in A union B, right, I'm looking for the number of elements in the set A union B, then if I start off by taking the number of elements in A, if I take all of this entire set, then I can say this is the number of elements in A, and then I take the elements in this set, the pink ones, so that's number of elements of B. Is that going to be equal to the number of elements in the union of A and B? No. Why? Because there is this middle term, this middle section, which has been counted twice. So we've counted this section, the elements in this part, this A intersection B has been counted, A intersection B has been counted twice. it was counted when I was taking the number of elements of A, and it was counted when I was taking the number of elements of B. So if I want to find A union B, what I can do is I can remove these elements, A intersection B, and now you have A union B, the number of elements of A union B. And so this part is inclusion and this part is exclusion, right? Now it won't be a principle, a general principle, if it only worked for 2 sets. So let's do a case with 3 sets. So I have, let's say, set A, set B, and set C. Right? A, B, and C. And now again I wanted to find out the number of elements in A union B union C. So I start off by my inclusion. Let's include the number of elements of A, let's include the number of elements of B, let's include the number of elements of C. And so these elements are simply coming from these circles here, right? So again, taking these elements and taking these elements. Okay. All right. So now what's the issue? I have these 4 other sections that have been counted twice, right? So this one, which is A intersection B, this was A intersection C, and this was B intersection C. So now I can go ahead and remove these because they were counted twice. So I remove A intersection B minus A intersection C, and let's just give them a different colors. Oops. And yeah, and so these terms are the ones that I'm writing now. So A intersection B, A intersection C minus B intersection C. And at this point, notice what has happened. We had this set which contained, so we included this part A intersection B, but we also included this middle part. But when I removed A intersection B from here, this part got removed. Then I selected all the elements from B. Then I had this part, I removed this intersection between B and C because I was counting it twice, but I removed this middle part again. So which means this middle part has been added thrice and then removed thrice as well. It was included in this, included in this, and included in this, and it was being added thrice, right? But again, it was also included in this and this and this, so it also got removed thrice. That means this part has been added and then subtracted from the sum. So if I want to include it, I want A intersection B intersection C, and so now I add the remaining bit, which is plus A intersection B intersection C, right? So notice that this is not just inclusion exclusion anymore, this is inclusion, exclusion, and then inclusion again, right? So this was my inclusion, exclusion, and then inclusion again. And now I can generalize this pattern to a set of 4 elements. So if I go to A union B union C union D, let's write that down let's follow this pattern and do this without looking at any visual diagram. So the first 4 terms are going to be A intersection A, number of elements of B, number of elements of C, plus number of elements of D. What are the next terms going to be? The next terms are going to be the intersection between any two of these, right? So which means we will subtract A intersection B, subtract A intersection C, A intersection D, B intersection C, B intersection D, and then finally C intersection D, right? At that point we will also add, so inclusion, exclusion, and then again an inclusion, and now we're looking for the intersection between three of these. So the first one is going to be A intersection B intersection C plus B intersection C intersection D plus what else? So if I remove B and include D here, so that's A intersection B intersection D, what else? Plus A intersection C intersection D plus what else? Am I missing anything now? So this should be, I'm trying to select 3 elements from 4, so 4 C3, and I think those should be 4 elements. So yeah, 4 terms, and I'm fine. And at the end, now that I've done my inclusion, then exclusion, then inclusion again, which means I will have another exclusion, which is the section A intersection B intersection C intersection D. And so this should equal to my sum, my union of these 4 elements, and you can check that visually, right? So if you check it visually, you will have, notice that you will have these 4 sets. Okay, I don't like that it didn't turn into a nice circle. Yes, there we go. And jump. So first you're including all of them, then you're removing the pairwise intersections, then let me do this. Oops, made too many shading marks. So then we included these pairwise intersections, over here, this one and this one. Then we removed at the intersection of 3 of them, so this one, and this is too difficult to see, but you get the idea, right? And then you just remove the very middle section that was added 4 times. That was added and then subtracted and then added again 4 times, so we just subtract it once. Okay? Any confusion? So if all of that is clear, then I can state the inclusion-exclusion principle for a set of n elements and be done with it, right? So here it is. Let's just state it. Perfect. So here's the inclusion-exclusion principle. If I want the union of, if I want the number of elements, so inclusion, exclusion principle. If I want the number of elements in the union of A from I goes from 1 to, let's write this neatly, the union of all the AIs where I goes from 1 to n, then this union is equals to first we sum up all the cardinalities or the number of elements of the individual sets, right? So the individual sets from I equals to 1 to n. Then in the next term what we do is we subtract the summation of pairwise intersections. So AI union, intersection AJ, right? And so now I have to look at I and J, and so I and J will basically start off from 1 1 is less than or equals to I, and then j has to be different from I, and so I can say j and then goes to n, right? And so I'm doing the summation for these pairwise intersections, and then on the next term I will of course do an inclusion. And so let's write that inclusion. That inclusion is something like summation ai intersection aj intersection ak, and the indice is going to look like, it starts off from 1 I, and then j is different from I, and then k is different from I, and they're up until n, right? Okay, and so I can write the general term now, which is plus dot dot dot. Let's write the general term. The general term is going to be something like minus 1. So it's going to be, oops, it's going to be, actually instead of writing the general term, let me just write the n term. So the last term in this entire thing is going to be minus 1 to the power something. So the last intersection of all of these elements, it's either going to be included or excluded depending on the number of elements. So when I had 2 elements, the last intersection was excluded, right? So the power was minus, so the sign was minus. When I had 3 elements, the last intersection of all of these sets was included. So for 3 it's plus, for 2 it's minus, and for 4 it was minus again, which means when it is even we excluded, when it is odd we included. And so a nice way to incorporate that is to just write n plus 1, because when n is even, then this power becomes odd and the sign becomes negative, and when n is odd, this power becomes even, and so the sign becomes 1 plus 1. And so I write the sum, the intersection of all of them, a1 intersection a2 intersection dot 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 intersection a n, right? And that's my principle. Right? And now the question is, why do we care, right? And let's do a example perhaps. Dun, dun, dun. You can think about, let's suppose, instead of these sets A, you can think about, let's say, set N, set A, oops, where is it? Yeah. So think about set A contains set A1 contains elements and that contains elements with property P1. For example, set A1 contains all the students that have taken the discrete math course, right? So some property P1. And set A2 contains elements with property P2. Set A3 contains elements with property P3, and so on and so forth up until set AN contains element with property Pn. For example, the first set contains the students who've taken the discrete math course. The second set contains the students who've taken the linear algebra course. The third set contains students who've taken some other course, right? And so on. So these are different sets that contain different students. So of course there's going to be some students who have taken both those courses, right? There are some students who might have taken 3 of those courses, and so on. And so if I want to look at the total number of students, so the total number of students, then what I'm looking for is students that contain that have the property P1, that have property P1, property P2, property P3, and so on up until Pn. That is all the students, not that these students contain all of these properties, but the total number of students that there are, right? So what I'm looking for is the total number of students. So A1 union A2 union A3 dot 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 AN, right? And so of course there's going to be students who've not taken any of these courses, right? So there's going to be students who are neither in, who don't have property 1, who don't have property 2, who don't have property 3, and basically the students who are outside this entire set. So these are students outside the elements that have none of these properties, right? So I can state the inclusion-exclusion principle. So if the total students is equals to n, then I can think about the students who've not taken any, who've perhaps not completed any courses, right? Dot 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 Pn is the same as n minus this union. So n minus n, P1 or P2 or P3 or Pn, right? And so basically what we're doing is we're subtracting. So this is basically equals to n minus, and you can think of this as the union, the number of elements in the union, A union A1 union A2 union A3 dot 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 An. And so you can rewrite this entire equality as n, the students who've not completed any courses yet are the students, total number of students minus, now I can expand this property, right? I can think of this as, I use the inclusion-exclusion principle. So first I will add all of the elements, all of the students who've taken at least one course, right? Who've, all of the students in some course, P1, Pi, I goes from 1 to n. Then I will exclude students who have taken two courses, Pi, Pj, right? So I is less than j, less than equals to n, less than equals to 1. Then I will include the students who've taken three courses, Pi, Pj and Pk. I goes from I is less than j, less than k, and so on up until I get to the last intersection, which is minus 1 to the power n plus 1, the students who've taken all P1 and let me see if I can P1. So yeah, and so these are the students P1, P2, P3 who've taken all of these courses, P and okay. And so this is the same inclusion-exclusion property, but being written in a different way depending on the property that you are looking at. Is that clear? There's a dot 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 here which I have not written, but minus dot dot dot. So another exclusion, then inclusion, then exclusion, and then so on. Okay, let's see if we can do an example here. Okay, any confusion so far? No, everything's clear. Okay, so let's do an example and then end this. So here's an example, and I'm not going to complete this example, I'm just going to state it. So let's say I want the number of primes, number of primes less than or equals to 100, right? Now we've done this problem through the lens of sieve of Eratosthenes, which is we list down all the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then 11 to 20, 21 to 30, and so on up until 91 to 100. And the idea was that if I start crossing off numbers from this list that I know are not going to be prime, so starting off with the first prime, I know 1 is not a prime, so that gets excluded, and I know 100 is not a prime, so that gets excluded. And if I start excluding the elements, so 2 times 4, 6, 8, 10, 20, 30, these elements get excluded, and then I start off crossing the multiples of 3, so 3 is there, but 6 gets excluded, 9 gets excluded, 12 I know gets excluded, 21 will get excluded, 15, and so on, cross off all the multiples of 3, and then do the same for the next prime number. The next prime number is 5, right? And so for 5, I take 5 and I remove the multiples of 5, so 20, 30, 10, 20, 30, 100 all get excluded, and these multiples of 5 also get excluded, right? And so we're removing the elements. Now instead of doing that, if I were to do the following, if I were to use the inclusion-exclusion principle, so I'm saying that I want the number of elements that are neither divisible. So property, I write it down in terms of properties, right? So property 1 is that it's divisible by 2. Property 2 is that it's divisible by 3. Property 3 is that it's divisible by 5. Oops, that's a very ugly 5. And property 4 is that they are divisible by 7. I don't need any other property, because notice that after 7 there is no prime up until number 10, and I don't need to check primes that are bigger than 10, because 100, the square root of 100 is going to be equals to 10, right? So I only need to check the elements that are smaller than square root of 10, right? Okay, and so I need only these 4 properties, and so I can write this equation down as this. I can say the number of elements such that P1 complement, P2 complement, P3 complement, P4 complement is equals to n minus number of elements Pi. So let me write it as summation n Pi plus summation n Pi Pj minus summation n Pi Pj Pk plus summation n Pi Pj Pk and Pl. And what is this equation telling me? This equation is telling me that now these are elements that are not divisible by 2, 3, 5 or 7, which means these are basically the number of primes. These are all the primes. If they're not divisible by 2, 3, 5 or 7, then they're going to be the number of primes. So number of primes of primes less than 100 is equals to the total number of elements less than 100. So total number of elements, you can think that's 101 if you want to include 1 or 100, and it's 99 if you want to exclude those numbers. So let's call it 99. And the remaining sum, so these are all the, so this is the number of the numbers, the total numbers divisible by any one of them plus the total number divisible by any two of them minus the total number divisible by any three of them, and finally plus all the elements divisible by all four of them, right? And so you find out these terms. Now these terms, I'm not going to explain how to do this. You can perhaps look at the book or try to guess yourself. How do you find all the elements that are divisible by any one prime number or any two prime numbers, any three prime numbers, or all four of these prime numbers, right? So in this set, basically what you will have is all the numbers that are divisible by 2, divisible by 3, divisible by 4, 5, and 7. And in this set you're going to have, the first set is going to be divisible by 2 and 3, divisible by 3 and 5, and so on. You will make these pairings and so on and so forth, right? And so if you can find these four numbers, then you, not four, but these will contain some pairings, different pairings. And so 4 numbers here and 6 numbers perhaps here. You find all of these numbers, you subtract them from 99, and that will give you the number of primes less than 100. And these are actually easy to find. You can look them up, or you can try to guess the pattern yourself. Okay, any confusion? Oh, okay, excellent. Then that's it for today. That should be, let's call it a day. Bye-bye. Fade to black.